now that we've seen center of mass, let's do some examples to see how we actually calculate this. So again, just to remind us, the position of the center of mass is dependent if it's discrete objects or continuous objects. So for discrete objects, it's simply the weighted average of the position of each one of the individual objects weighted by its mass divided by the total mass, where again the total mass for discrete objects is the sum over all the individual masses. And then for a continuous object, it's then the integral of the position integrated over dm, where again dm is going to take on the geometry that the problem actually has, divided by the total mass, where again the total mass now is the integral over all of those differential masses. Now, before we actually start, first thing to point out is as long as we're working in something like Cartesian coordinates, such as this problem, the nice thing is that even though these are position vectors, that position vector will then be broken up into different coordinate systems, or different axes, which basically means that if I'm looking for the position of the center of mass, I have to only calculate its x position, its y position, and its z position, and then record that all as either a position vector in ijk, so unit vector notation, or in point set notation. But when I calculate the position of the center of mass, I don't have to do all directions at the same time. I can concentrate on one particular direction. Now, the other thing that's going to be true is some of these directions, they will have the position of 0. So basically, one thing we always going to look for in problems like this are symmetries, which basically means that, for example, in this case, the first problem we're going to look at is here I have all the masses along the x direction, nothing along the y direction, which means that since all the masses are concentrated along the x direction, there will be no deviation away from that x-axis, which basically means that by automatically looking at this, we can say since the symmetry of the problem is all along the x-axis, there will be no mass pushed up in the y direction or pushed down in the negative y direction, which means position of the center of mass in the y direction is simply 0. So we would simply say, by symmetry, the y center of mass position is simply equal to 0. Which means that if I'm looking at this particular problem where I have 3 masses, m1, m2, and m3, where m1 is 5 kilograms, m2 is 2 kilograms, and m3 is 4 kilograms, where m1 is away from the origin by a distance r1 equal to 0.5 meters, and r2 is 1 meter away from the origin, then we can say that all of its mass, again, being concentrated along the x-axis, then we only have x position for the center of mass. So in this case, we only need to know its x position. Now, again, by looking at these, this one has 0 position. This one has 0.5 meters. This one then has 1 meter away. So okay, what we want to determine here then is what is position of the center of mass. And again, position of the center of mass in this case will only be determined by its x location, since its y location is simply going to be 0. Now, since these are 3 different point masses, we would then say that we would use the first expression to then determine exactly the location of the center of mass. So let's use that. Okay, in Cartesian coordinates, this thing is going to break up into components, which basically means that when we're determining the location, we only need to determine the x center of mass location. So according to this, this is then going to be the mass of the first one times the position along the x-axis of the first, plus the mass of the second times its location along the x-axis, plus then the mass of the third times its location along the x-axis, all divided then by the net mass, which in this case is going to be m1 plus m2 plus m3. So from here, we know that x2 is simply equal to 0, x1 is equal to r1, and then x3 is equal to r3. Thing to point out here is, again, since this depends on the coordinate system, r1 is actually going to be a negative quantity since it points to the left from our origin. So this is going to become what? Negative m1 r1 plus m2 times 0 plus m3 times r3, all divided by m1 plus m2 plus m3. Anything times 0 is simply equal to 0. So in this case, we simply have to plug in our numbers. So this one becomes equal to negative 5 kilograms times 0.5 meters plus 0 plus then 4 kilograms times then 1 meter all divided by the net mass. Well, the net mass in this case is then, what, 11 kilograms. Plug in our numbers. What we find in this case then is the position along the x-axis then is 0.14 meters, which would put the center of mass location roughly about here. This would be the center of mass location. Good. Let's do another example. So the next example says that we have a T-shaped object where the object has uniform density. So we again want to determine what is the center of mass location of this object where we have this thing. So according to this coordinate system, if this is the y-axis, this is the x-axis, and all of these sides are side A. So this is A, 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 and A. What is the location of the center of mass? Now, again, first thing we're going to look for is this idea of symmetry. So in this case, as long as all of these objects have exactly the same amount of density, what that means then is since these have exactly the same sizes, this is A by A, this is A by A, this is A by A, this is also A by A, well, that means that the mass of each one of these objects is identically the same. So this has mass M, mass M, mass M, and mass M, which means that, according to this coordinate system, since this line bisects it, I have as much mass on this side as I have on this side, which means that the location of the x-center mass should be 0, because I have as much mass on this side as I have on this side. Now, in the y direction, that's of course not going to be true, because I have more mass above the positive y-axis as opposed to nothing in the negative y-axis, which means all the center mass is going to be somewhere near the top. And again, since this portion here is 3 times more mass than this portion, what that means is that the location of the center mass is going to be somewhere about here. It's going to be my location of the center of mass. So again, we would say by symmetry, automatically we know the x location of the center of mass is simply equal to 0. So now we just have to state where that y portion of the center of mass is. Now, even though these are technically continuous objects, these are what we would call regular objects. So an object such as this paper, as long as it has a uniform density and as long as it has a uniform shape to it, it turns out that all the mass is concentrated at its geometric center. So if I'm looking at this paper here, or if I'm looking at this ruler here, again, as long as this thing has uniform density to it, that means that the location of the center mass will be at its geometric center. Now, in these cases, since all of these are simply squares, they all have uniform density. What that means then is the location of the center mass of each of these objects will then simply be at the geometric center of these objects. Which means that this distance along here is going to be a over 2. This distance to this top line is then going to be what? A plus an extra a over 2, which is then 3a over 2. So even though this is made up of continuous objects, these continuous objects fit the bill of a regular shaped object, which means we can actually treat them as a discrete object. So even though this is continuous objects, I can treat these as simply 4 different point masses and use that same expression, i.e. the first one, for discrete masses. So using that, what this means then is that the y portion of the center of mass is going to be equal to the sum over all the masses weighted by its position. So this is going to be what? M1 times Y1 plus M2 times Y2 plus M3 times Y3 plus then M4 times Y4, all divided by the net mass. But again, since each one of these has exactly the same amount of mass, this is simply going to be divided by 4 times the mass, where M here is simply the mass of one of these objects. Now again, since each one of these has exactly the same amount of mass, it means this is simply M, 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 and M, so those M's are going to cancel with this M. So it's going to be the same thing then as 4 times then Y1, or 1/4, sorry, times Y1 plus Y2 plus Y3 plus Y4. Now the other thing to note is this Y, and this Y are all exactly the same. They're simply 3/2 of A. So, since I have 3 of those, this is the same thing then as 1/4 times 3 times 3/2 of A plus that last one, which is simply then 1/2 of A. So, the A's are all the same, so I'll factor that out. So this is the same thing then as A divided by 4 plus then 9/2 plus 1/2. Which is the same thing as 10/2, which is the same thing as 5. So this is then equal to 5/4 of A. So the location of the center of mass is then equal to 0, 5/4 of A. Now, does that make sense? Well, again, 4/4 of A would be exactly A, so that would be at this location. 6/4 of A would be at 1.5 A, so that's the same thing as this location. So 5/4 of A would be right here, which is exactly where we expected it to be. A little bit above that center point, but not quite all the way up to the top. Let's do one more. The last one, we're looking at a cone. So a 3-dimensional cone. And let's integrate over this guy. So this says, determine the center of mass of a machine part that is a uniform cone of height h, of radius r, which is inverted. So here's my cone. So along this direction, this thing has a height of h. And here, this thing has a constant radius of capital R. We want to know what is the location of the center of mass of this object. Now, in this case, we didn't give a coordinate system, so we can choose our own coordinate system, and we're going to choose our coordinate system to make this thing as simple as possible. And the best place to put our coordinate system is actually right here. So let's call this our x and y axis, so that the tip of the cone is directly at the origin. And then let's put the z-axis along the center of the object, so here. So why does this make this as simple as possible? Well, if I was looking down along the z-axis, what you notice in this case then is what? This thing would be a simple circle. So here would be my circle of constant radius of r, where this then would be my x-axis, this would be my y-axis. And for the same reason as before, in this case, since I have as much mass in the positive x-axis as I have along the negative x-axis, and I have as much mass along the positive y-axis as I have along the negative y-axis, again, assuming that in this case my object has uniform density, what that means then is the location of the center of mass in both the x and the y direction are simply equal to 0. They're directly at the origin. So in this case, again, x center mass is equal to y center mass, which is equal to 0. Which means the only place we have to determine the location of the center of mass is along the z-axis. Here, since I don't have a lot of mass down here, but I have a lot of mass up here, we should expect then that the location of our center of mass is going to be somewhere pushed closer to the top. Since this thing has all its mass concentrated basically just in the z direction, let's just look at what's happening in that direction. So let me redraw this as simply a triangle. So here's my cone, where again this is my z-axis, and let's call this arbitrarily the y-axis. Now, this now constitutes a continuous body, which means that to determine this one, we would then have to integrate z integrated over the total mass. So in this case, we do have to actually do an integral. Now, from here, we have to determine what type of symmetry we actually have. Well, in this case, since we're looking at actually just the cross-sectional of this guy, we have to look at the entire differential volume. So what we're going to do in this case then is what? Chop this thing up into a bunch of small volumes. So this section here, I'm going to chop across here, where this thing has a total volume of dV. Now, since I'm chopping this into a small section, this thing then has a width to it of dz, and this is going to happen at a height above the center, which we're going to call simply z. Now, if I drew that over here onto this cross-section, that means is basically I'm drawing a little circle here. So I'm drawing a disk, where this disk then has a thickness of dz. So that this has a radius of little r, which is the same as this radius across here of little r. So ultimately what that says then is that this differential volume is going to be the same thing then as what? The area of the disk times the thickness of that disk. So the area of that disk, since this thing is simply just a circle, this is going to have an area of pi r squared times the thickness then of dz. So this is my differential volume. So my differential mass then, dm, is then equal to the density times that differential volume, which is the same thing as that density times then pi times the radius r squared times then dz. Now, other thing to note is that what? Even though this has variable of r is not independent of z. So what do I mean by that? What I mean by that is what? If I took this little wedge that I'm cutting out here, and then I move it upward, what happens in this case then is that r is going to increase, and z also increases simultaneously. So these two things are actually not independent from each other. So what I have to do then is determine how does r and z actually relate to each other. And the way we're going to do that is basically by looking at similar triangles. So in this case, what I can say is this distance across here is capital R. I know, again, this total height across here is h. So I can say that r to h is related to little r to z. So this tells me then that what? Capital R divided by h is equal then to little r divided by z. So if I solve this for little r, this tells me that little r is in fact equal to capital R divided by the total height times z. So in this case, I can turn little r into then z. Good. So let's put all these pieces together. So it's going to be equal to then the integral of z times dm, which is now going to be rho times pi times little r, which is then capital R divided by h, times z, quantity squared, dz divided by the total mass of the object. So let's do it that way. So in this case, we're going to integrate over z, but here we're going to integrate from the bottom point, which is going to be z is equal to 0, to the top point, which is z is equal to h. Now we got the problem set up. Let's go ahead and get rid of this. And then perform the integral. So let's pull out the things that are constant. So rho is constant, pi is constant, r squared over h is also constant. So here we then get that z center mass is equal to then rho times pi times r squared divided by h squared times m, all times the integral of then z cubed dz from 0 to h. So now what? So good. So here we have the integral of r cubed, or sorry, z cubed dz. Integrate that. That becomes r to the 4th divided by 4. Evaluate it from 0 to h, which means that that is just going to become h to the 4th. So this is going to become rho pi r squared h to the 4th divided by 4 times h squared times n. Now rho, again we know rho is equal to the total mass m divided by the total volume. So what's the total volume in this case? Well, the total volume then is just going to be the integral over this guy, which basically means that this is going to be equal to, so let's do m, or the total volume. Where do I want to write that? I'll write it over here. So good. We can then say that the total mass is equal to the integral of dm, which is rho times then dv, from 0 to h, which is then going to be the same thing as rho times r squared divided by h squared times pi, integral of z squared dz from 0 to h. So it's going to be the same thing as rho r squared pi h cubed divided by 3 times h squared. So good. So let's go ahead and plug that in for the total mass. So finally, what we're going to get is that what? So plug in all of our stuff. We get in this case then that this becomes 3/4 times h. So finally, we can then say that the position of the center of mass of this object, our center of mass, is equal to 0, 0, 3/4 of h.